right, so here, let's look at E. E will probably have something different. All right, so this is what, let's say about 6 of a difference. Well, this is less than 2. So this width is, 4 times as much as that. And so, that varying width could like throw people off, especially if you want to like visualize this along the number line. You could, it will look odd to people. Now, hard to make is somewhere in between the two in terms of the width and the counts. We look through, I don't see anything that's too wonky on the distribution of counts. What, 300 is probably the least. And the advantage on this technique is that this tries to preserve the mutual information that's there. So you think of correlation, that's not exactly the right way to think about it, but in your head, think it tries to preserve something like correlation between the numbers. All right, so what we're going to do next is that we're going to use each of the 3 data prepared data sets we have. And we're going to build Bayesian networks. And then we want to decide which method was best. So what I want to impress upon you with this is that when I go through my process of train, validation, then test, your data prep step is more important than the actual model structure. If you build a lot of models, let's say supervised learning, whether it's categorical or numeric targets, one thing you will notice over and over and over, if you do this professionally, is that models tend to have like similar performance levels. That you'll get similar mean absolute errors across the board. Now you will have some model structure that will be better, some that will be worse. The model, in my opinion, your model structure is not as important as the data going into it. And so your data prep phase should absolutely be a critical double check, train, validation, test part of the process when you consider what to do. All right, so now let's go ahead and build the Bayesian networks. All right, so to build the models, we're going to go through and run these algorithms. If I remember correctly, I use a try. Yeah. So here are the different ways to train the model.
Sounds like a you problem.
Most of the time, hill climber or taboo ends up being the top for my professional work.
No, I'm not.
Got it.
Is somebody trying to ask a question? I'm going to mute everybody in Zoom.
I get this done by Wednesday.
Yeah.
I don't think they know.
I told the girl I didn't want to hang out with her today.
All right. If you have a question for those who are with us via Zoom, please type it in the chat and I'll get to you. All right. So we're going to go through. We're going to build the models. Now you'll notice that I'm doing different algorithms to fit the model, and I'm choosing different prepared data sets when I'm doing this. I'm executing this via do call. So if I want to call a function using a character string, we want to use do.call in R, which I think the computer programmers will be like familiar with that. Now, this next phase, what I'm doing here is I'm double checking to make sure I get the best arcs going. You don't really have to do this, but I like to double check that I have the arcs going in the right direction. And so here it's just going through and just seeing if I can get something better going. All right, so what this does, this makes sure that I don't have any non-directed edges. Because for interpretation, I like to have an arrow pointed. So what this will do is if I have an edge that does not have a direction, because not all of these algorithms are always directed. So some of these will give non-directed edges. For interpretation, for presenting to clients, I find it works better if I have an arrow pointing a direction. So here I'm just going through, hey, go through and try to set a direction on it for me. And here is to go through and double check to make sure I get the best direction possible. When I'm doing Bayesian networks, the most common mistake I can have with an arc is that it's pointed in the wrong direction. And that's because of the proportional relationship between conditional probabilities. The three mistakes we can have with arcs is that missing one when we should have one, having one there when we shouldn't, or having it in the wrong direction. And this here, I'm just trying to make sure I don't have anything pointed in the wrong direction. All right, so now what I want to do, I want to use the Bayesian information criteria to check to see how the model performs. Now, you'll notice in this example, I'm not actually using the train test split criteria to evaluate the model. The reason for that is if I'm doing a Bayesian network, all variables are target variables potentially, all variables are potentially predictor variables. If I want to evaluate it using a train test split paradigm, I have to choose which, after I get my validation set pulled out, I have to choose which ones are going to be target, which ones are going to be predictors. For this example, in the classroom, I don't have a clear set idea. So therefore, I'm just, running this on my training sets. And so here, I'm just going through and I'm going to set up a matrix to hold the values. I'm going to have rows correspond to the algorithms and then columns correspond to the data prep. And I'm just scoring the BIC across the board. And so here we can see the results. All right, now remember with the Be and Learn package, AIC and BIC are reversed. Normally, when we do AIC and we do BIC, the least value available is our best one. That's the schema. The author of the Be and Learn package flipped it around. So we want the maximum possible. All right, if I'm talking about the maximum, what would be the best choice? It would be one of these models over here. So you look through, you'll notice that these have all got the same values here. You'll also notice that these are greater than the other. So that's a sign that I'm choosing, if I'm getting like ordinal, or the order of the algorithms are the same across all of the different data preps, that's a sign that I'm choosing the right algorithm. This is performing pretty well. And so then it looks like on this one, interval would be the way to go. And quantile would be the least for this particular example. And so we'd want to choose one of these. The next step that I would take if this was a real project, I would look at the graphs and then I would choose which of these here gave me the model that I felt made the most sense. I would use a mixture of subject matter knowledge and this data to say, hey, I'm going to go with this model for actual launching.
What are you comparing to find the score? Like you said that you're applying it for your training set, right?
Yes.
So you have a model that was built with your training set.
Yes.
And in order to get an score, we have to compare this model with some other. Like
Oh, okay. So yeah, this is different. So we are, is log of n times number of parameters, and then the log likelihood. We have estimated log likelihood minus n times data size times the number of parameters. And this is how we're scoring this. So it's using, it's making an assumption about the distribution. So the distribution is based off of the like chi-squared table test, gives us this likelihood. We take log of the likelihood, then we subtract this penalty term. Now, something to realize is that the regular BIC is this, but in this package, it's that. So we want the largest value we can get. And so here, it doesn't actually check against like residuals. This is, and if I wanted to do AIC changes this to a 2. And so what this does, this looks at, this part checks to see how well does it fit the model. And this this gives us a penalty for having more parameters. So this gives me a penalty for having a more complicated model. And then this gives us like the log likelihood is if it's a larger value, that says that it's a better fitting under the assumptions. But good question. All right, so after I choose my model, I want to go ahead and plot it. And now something you will notice as I go through with these relatively simple data sets, if I was to plot each of the models, you would see redundancy. But the model that we get here, at least is in form of structure, realize that the tables have not been fitted yet. So far, we have only fitted the shape of the graph, like which variables connect to which other variables is all we've done. And so this is the model that we end up getting off of this. Now, remember that if I want to make a prediction on something, or let's say that I know what the value of D is, and I know the value of A. I know the value of D, I know the value of A. I can, in fact, estimate or predict any other variable. So think about it like this. If I know the value of D, that changes the conditional distribution of B, correct? If I know, if I have a conditional distribution of B, by Bayes' theorem, that changes the conditional distribution of C. Now, I know A, and I have a conditional distribution of C, changes the conditional distribution of F. Having a conditional distribution of F changes the conditional distribution of G. And so if I know D and I know A, and I want to know G, I would actually get like a discrete probability distribution for it. But once I have that, I could go through and see what is likely to happen. I can make an informed decision off of that. Now, it's not a very precise way if I've discretized, but it's very nice in that if I, next time I receive data, I receive just C and E, I could go through and run through the rest.
A, B, C, D, those are columns in the data set.
Yes.
So if you had different attributes, you would see the actual attributes, not just a representation. Okay.
So let's say, it was for tests. Let's say that A is American history, B is botany, C is chemistry, E is economics, F is finance, G is global history, and D, what would be D? Discrete math. There we go. That could be a model, right? Any other questions?
Would it be possible to, not to have an arc between the nodes?
Yes.
So what that means that there is no, the module has not found any relation between,
Yes.
so.
Yeah, so let's say that this one arc between D and B is gone. Then that model would conclude there is no statistical relationship between D and the other variables. And we could also have it like two subgraphs.
That happened when I use the full data set.
Yeah.
It's all connected, but when I start using some samples, so like 2 or 3 disconnected.
Yeah.
Right.
Yeah, that can.
This information for to create relation.
Yeah, so there, what would happen is if D was off by itself, then what that's saying is observing all the other variables. Let's say I knew a fixed value on all of these, it would not change the value of D. That D would be whatever the distribution is of D by itself. That's what I would have as like my predicted value. It would just be like the mean. All right, the next thing I want to talk about is controlling the arcs when we work with Bayesian networks. All right, so the point of this part is if I'm building a Bayesian network and I know the direction of the variables, I need to take that into account. So everything we've done so far with Bayesian networks, we were just letting the algorithm just run free. Just let it go, let it do it, and we're not going to worry about, does it make sense? Does it make sense to have ice cream predicts the temperature of the day? We know that doesn't make sense, but when it comes to running the algorithm, the data may say ice cream predicts temperature, when we know that temperature would drive ice cream sales. So what we want to do is when we build our model, we want to set up either a blacklist or a whitelist for the arcs. The blacklists are ones we say do not include. The whitelists are the ones that have to be included in the model automatically. And so this will improve our model in terms of making sure it makes sense in terms of real life. It'll make it easier for our clients to accept the model, make sure it jives with their understanding. Also, it will improve computation time. So if I go through and I say that these arcs must be there, then what the algorithm is going to do, it's going to immediately slap those into the model first and foremost. This can greatly reduce the number of tested arcs that will be computed through by the algorithm. Also, if I put in a blacklist, those arcs will not be considered, and so it will speed up the process. All right, so once again, we're going to use the groceries data sets from the A rules package. And we're only going to use the 10 most frequently purchased items just because, I want to keep it fast, keep it moving. All right, so I'm going to take the groceries data set. I'm going to convert it to a matrix. So it'll be in the matrix format. This is the format I need if I want to do like matrix multiplication. But this isn't the best format for most data science work. We actually want data frames for almost everything. So then I'm going to convert it to a data frame. So the steps are convert it to matrix, then convert it to data frame, and now it's in the format that we can use. And we'll go through and use the make names function. All right, what this does is that this converts all the column names to syntactically correct names. If you work in R enough, you'll find that some functions will not accept spaces or special characters in the column names. The names of objects in some functions must be proper syntactically correct names. The make.names function will do this. This isn't my favorite way to do this. I actually prefer using the Jandar package That's what I actually use at work, but it's not base R, so I don't, I want syntactically correct names, but at work, I don't use this one. I use the janitor package. Now I'm going to go through and I'm just going to like resort things by column sums and row sums. The reason why I'm doing this is because I'm only going to limit things to the most frequently purchased items. And if I have a smaller data set, I'll do this in real life to help me kind of spot trends that might be coming up in the data as I look through things.
Professor,
Yes.
we cannot see the latest screen, Professor. We are
Oh,
still
you cannot see
the
that.
previous- Yeah,
I'm
yeah.
selfish and I'm not sharing. All right, so then let's hit new share. And can you see it now?
Yes, yes.
Thank you so much for saying something. All right, so we're talking about controlling the arcs and edges in a Bayesian network. So what we're going to do, our primary way of controlling these things are to, before we build the model, we're going to say include these, exclude these others. We use a whitelist to include the ones we want to absolutely have 100%, and we have a blacklist for the arcs that we do not want to have. And we're using the groceries data set from the Aic package. We're converting that to a matrix. And then we convert the matrix to a data frame. This step, I am making the columns syntactically correct. Now here, I'm going to go through, I'm sorting the data just so it's more organized. It's easier to find which ones are the most common. And I'm going to focus for this example only on the 10 most common, because otherwise we'd have just a huge network. And I went ahead and resorted everything because when I get rid of the columns, the row sums can change. Now, remember that the Learn package does not like numeric values as much as categorical. And the Learn package will treat everything as Gaussian regression, standard linear regression. The grocery data is count data. So what I chose to do on this one, I went ahead and converted everything to factors. So that means that a count of 0 is the first level count of 1 is the second level, and so on. Now, this is not ordinal data. The Learn package does not like ordinal data. A better way to approach this would have been to have gone through and bend values together, like 0 by itself, then like 1, 2, or 3 in one bin, and then so on. But I just went ahead and ran this just to get it going. You know, the purpose of this part of tonight is not about the data prep. It's about the controlling the arcs. All right, so now what I want to do, I want to build a Bayesian network without determining, without preset restrictions, requirements on the model for the arcs. And so I'm going to go through and I'm going to run the hill climber algorithm. And you notice I'm not setting a whitelist, I'm not setting a blacklist. I'm just saying whatever the data says the arc should be is the arcs that they should be. And we get this model here. We get rolls and, you know, drives sausage, sausage drives soda and shopping bags and other vegetables. And we can see that we've got all these other items on here. Now, one thing I want to point out is that I use the ellipse shape. This does a much better job of plotting than the default circles. The default circles take up more vertical space, and it's harder to see the entire graph. All right, so now what I want to do, I want to set up a whitelist to tell R to make sure first and foremost, these get added into the model. Then after those are in the model, go through and test all the other possible models. So when the algorithm executes, it's going to go through and it's going to make sure we never have a cycle. So in this package, when we do a graphical model, we will never have any cycles going around and round. It's always directed acyclic graph. So after these are in here, this will force several things to not be even considered. They won't even be evaluated. So this can greatly speed up the process because these are already here. Everything that would create a cycle is not even considered. And the more I put in, the faster this will end up being. How we set this up, our whitelist, is it's going to be a 2-column data frame. We have the first column is going to be our from, and our second column will be to. And we need to name first of all, we need to put it, from is the left column, to is the right column, and we need to name the data frame off of this. And so now, I'm going to run the algorithm, and I'm specifying that I want sausage to lead to root vegetables. I want rolls and buns to lead to other vegetables. So let's see how that would change. All right, so we want sausage going to root vegetables so that we're saying we want it to go straight over here, and rolls and buns, we want to go to other vegetables. So it's going to skip over this. Let's see how the output changes. So you'll notice that up top here is rolls and buns. Now what's up top is whole milk. So some things have shifted around. Now what we want to do, we want to exclude some arcs to be in our model. All right, so I want to exclude bottled water going to soda, and I want soda going to bottled water. So I have subject matter knowledge. I believe that if somebody is buying soda, they're not buying water. If they're buying water, they're not buying soda. And you'll notice I have both directions included. So if I was to go just bottled water to soda, it could be possible that soda could have an arrow going to bottled water. Let's see what happens. All right, so now we can see that rolls and buns goes back up top. All right, so next, what we want to do, we want to include the ones that we said 2 models ago had to be in there, and we want to exclude the ones from our last model. As I go through and I plot, here's what we get. All right, so now that is controlling the arcs when we set things up, like before we've actually fitted the model. Next thing that we can do is that we can use the set arcs function, and we can use choose direction to adjust what's going on. What choose direction does is it takes the graph that's handed to us and it double checks to see, is the arrow pointed in the best direction? And so this is a way for it to double check, do I have the best model possible? So the choose direction function will let's just add an arc when we know there should be one. So let's say that I built the model, but I'm like, oh crud, I forgot something, or something should have been there. I don't want to go through the full process. I can use choose direction to build it or to modify it, or we can double check to see if an arc is pointed in the right direction. So choose direction. If the arc, if two variables do not have a connection already, it will see, is there a connection? It'll try to set up a connection without violating the directed acyclic graph part. And if the arrow, the edge, or the arc between them already exists, it'll check to see, is that the right direction? And so here I'm just telling it to go through and check to see if soda and shopping bags is in the best direction possible. So here we have, where's soda and shopping bags is here. Is this actually the best way to have it? And so choose direction is going to go through and check to see if soda to shopping bags is right, and the algorithm concludes that it is. Usually it will be consistent with what's already there. Now, if I want to add an arc after it's already built, I can use set arc. It's better to have it there in the first place usually. Now, something that will happen, let's say I build the model and, oh crud, I forgot an arc. I need to put a connection in there. I'll walk up and I'll try to run it. If I do not change the default setting on check cycles, it's going to check to make sure I don't violate that directed acyclic graph part. Well, let's say that putting that arc creates a cycle and I don't catch it, I don't do anything about it. That can cause problems in fitting and other aspects of using the function. And so it's best if we can to have it already in there when we build the model. So now here's how the model changes. Another option that we have is to switch the direction of the arc, reverse.arc, kind of obvious. So here it was what, tropical fruit and soda. And so previously it was tropical fruit going to soda, and now it's reversed. And we can also drop an arc. So once again, tropical fruit and soda. And you'll notice that the arc between them is gone. So this way we can adjust it. Now, if I've already fitted my models, or if I've already fit the model, and so I've got either contingency tables or the regression models built up, if I change the arcs, I need to go through and refit the model, that aspect. Any questions about this? All right, then we will move on to the last topic. Let's see, this is interfacing. All right, so something about graphical models in R is that there are tons and tons and tons of packages in R that will do graphical models for us. Something that is, so R's greatest strength and its greatest weakness is that it's open source. So there's all these people who have gone through and built packages for special reasons, but they overlap with each other. Well, there's substantially a lot of packages that have similar functions, similar purposes, same name of functions, same names of data sets, but there is a difference between them. And sometimes these packages, of course, for what you're doing, one will be better than the other. If I have an object in R and there's another package that has functionality I want to apply to that object, sometimes I can, sometimes I can't just pass it directly, depending on how the package authors have built stuff. In this part of class, I want to talk about basically taking something in the Be and Learn package, convert it over to another package's format so we can invoke that other package's strengths. Or other way around, take something that was an object from another package, convert it to a Be and Learn package object so that we can use the Be and Learn package's strengths. And so this is a good way to leverage things, and not, so that way we don't have to code things by hand. It's already there for us. There are a lot, and I mean it, a lot of specialized packages for working with graphical models in R. I mean, there's just a ton. Having some trouble with my mouse. Here we go. There's a bunch. And each of them have different strengths and advantages and disadvantages. And so, and also packages will have different object classes. If you're working in spatial statistics, generally speaking, spatial statistics from an object from one package transfers over to other packages really well. The R community has put a lot of effort in spatial statistics to have consistent object storage formats. The graphical packages have not gone through this rigor. Now, if you want to, you can sit down and fix it yourself. It's open source. We're all welcome to do it. But really, we just want to do our projects, right? We want to get paid as data scientists and go do stuff. All right, so we want to move between packages.
Can you please share the new screen?
I had trouble hearing you.
Can you please share the new screen?
Oh, share the new screen. All right, that would be a good idea for. Can you see it?
Yes, thank you.
Okay. All right, so the examples that are from this, I copied and pasted much of it from the beandlearn.com website. Now, the author of the package, he wrote 2 books on the package, and here they are, if you want to go and get them. The book user one, so this is in the Use R series of books in the Springer collection, and we can download this one for free as students at UCF. So that's an advantage of that. It's shorter and briefer than the one that's through CRC Publishing, but the one through CRC, their books are usually pretty high quality. They're edited pretty stiffly. The one from the CRC publisher is a better book. It's a more complete book, but there is substantial overlap, and there's substantial overlap with the website. So, I have worked through both books. I've ran every bit of code for both of them, and I've worked through much of the website. There's a lot of overlap. All right, so what we want to do is we want to interface the Be and Learn package with the Deal package. All right, the Deal package is one of the oldest R packages for structure and parameter learning. It supports conditional linear Gaussian networks. All right, so here the Deal package will work with continuous data only. It just wants continuous values. It doesn't want discrete ones. It only does hill climbing for us, and it does a posterior score followed by posterior estimates of the parameters. All right, so what we want to be able to do is export a network structure to Deal. So let's say that I have a Be and Learn object. I want to take it and put it into the Deal package format. Now, this is an older package. It does not have separate classes for network structures and fitted networks. All right, so one thing to remember when I'm working in the Be and Learn package is that I have the structure of the graph, and then later down the road, we actually do the fitting of the model itself. Like, what is the actual connection mathematically between variables? The deal package does not make this separation. So it's not possible to export a network structure that does not have a data set with it. All right, so what I'm saying here in this is that if I know the graph, but I don't have the data sets, so let's say I'm using subject matter knowledge, but I don't have data for my graph, things are not going to work out. So I have to have data and the actual model structure. Also, Deal does not support partially directed graphs, so the graphs must be completely directed. Something that's nice though is that the model string representations are the same. And this is by far the easiest way. The model string representation of a Bayesian network is by far the easiest way to convert between packages. And that's true across the board. And so the model string function is in both packages. And so we can use as network in Deal, which performs much like model to network in Be and Learn. And so what we do, we take the character string, drop it into as.network if I want a Deal object back. And I put the model string into model to network if I want a Be and Learn package object back. And so here, this is my model string. So here is what the string looks like itself. So this is how we can represent a Bayesian network. What this is saying is that hist does not depend on any variable. HRBP does not depend on any variable. Going down the list, we see that LVF depends on hist. If I go, and so whenever I see the vertical conditional probability bar that says the first variable depends on the second one, just like in conditional probability. When I see something like this, you see the colon between there, that is saying that VMCH depends on both of these. Now, if you are serious about mathematics, one thing that you will jump to is do we have a unique representation? No. The computer system will accept any permutation on the order of these relationships. I can completely reverse it. I can shuffle it. I'll get the same result for the graphical model. So we can have multiple versions of the string represented. Yeah, so here, the node ordering of alarm, what this function does is that this gives us a partial ordering between the nodes based off of the arcs. And so here, hist is coming first, then HRBP, PAP. Now, the partial ordering is not unique from a math point of view, but that's okay. And here, just to make sure that as I work through this, I get consistent output, I went ahead and put the ordering on this. That way, as I do my fitting, things are more likely to be consistent. Now we can import a network structure from Deal. So what we did here, what I'm doing is I have this model from the Be and Learn package. I want the deal version. To do that, I get the model string out, and then I pass that model string and the data sets into the as.network function within deal. And so this will convert that Be and Learn package object to the deal package format. Now let's go the other way. What I'm going to do is, here is a model that I want that's in the deal package. I get the model string, and then I use model to network. Boom, I've got the Bayesian network. And so this way I can go back and forth. So let's say I had older code that somebody at my organization was using for the deal package. I could invoke the power of the Be and Learn package. And you'll notice that when I'm working with deal is older, it's not as well established. I'm not getting as much output from it. When I have the Be and Learn package, you can see that more stuff is happening. All right, now the Pcalg package. This is a versatile package for structured learning. It implements both score-based algorithms and the greedy equivalent search and constraint-based algorithms, such as PC. It is one of the few R packages that can handle discrete data sets as well as continuous for graphical models. And so what we're looking to do is export a network structure to Pcalg. All right, so to be able to import structures as implemented in as.bn. All right, so what we do for this one, if I have a Pcalg object, I pass it to as.bn, and it will convert it over to the graphical format that I'm interested in. And now these functions, one of the reasons why this is nice is that I get additional statistical tests for me to work with that aren't available in other packages. This is a major reason why we'd want to use this package. Now, something that's kind of a pain in the neck about this, if I'm working with discrete models in this, the levels of the variables need to be coded as integers 0, 1, 2, 3, 4, and so on. And so to do that, what I'm going to do is, when I have a factor, I use as.integer. So under the hood, anytime I have a factor or ordinal factor in R, under the hood, it's actually stored as 1, 2, 3, 4, 5, and so on. And there's a dictionary connecting the two. Well, if I use as.integer, it'll convert it over to that number for us. Pcalg wants it to be 0, 1, 2, 3, 4, subtract 1. Boom, we got it. And so now I can get sufficient statistics. I can fit the model. And we've got plenty of things I can work with to get things going. Now, the plotting kind of sucks, but it's an available option if you do like it. So we can plot the connection between variables. And after I have a Pcalg object, I just use as.bn to convert it over. Now, when I do this, this is going to convert over the model structure, not the actual fitted contingency tables, not the linear regression models. Unfortunately, importing fitted Bayesian networks into Be and Fit objects is not supported. And it's possible that if I use Pcalg, I could get a cycle in my graph. And this function will automatically check to see unless I suppress the checking. All right, the graph package, this is a pretty big one in the R community for graphical models. This is part of the bioconductor suite of packages. It is a very popular package for graphical models, both directed and undirected. It has good number of algorithms for random graph generation, centrality statistics, graph distances, nodes, arcs. If you are a graph theory person, you're probably going to like this package a lot. And it connects to the rgraph viz package well, which is the one that we want to use for when we want to really get the most out of our visualizations. Major objects are GraphNL objects and GraphAM objects. So the difference is that GraphNL encodes a graph as a list in which each element refers to one of the nodes in the graph and contains a vector to the children. GraphAM puts things as an adjacency matrix. AM stands for adjacency matrix. Now, this could be a large sparse matrix, so there could be some problems with that. And so if I want to convert over, I put it as GraphNL, which makes it the object is stored as a collection of lists. And then here, make it an adjacency matrix. And both techniques will take a BN fit object or a BN object. So BN, remember, is only the graph structure. BN fit is when the actual contingency table has been fitted and or the regression. And so we can, fit a model, convert it over, and we can convert it over either way. All right, so that was how do we take a BN_learn package object and put it into the graph package format. Now we want to go in the opposite direction. Once again, what we're going to want to do is we're going to be working with the strings, the model strings over and over and over. So I'm sorry, I apologize. It does it for us automatically. I can drop GraphNL and GraphAM objects straight in, and it will work out the details for us. Quick and easy peasy conversion. Now, something I'm doing here is you'll notice that this is a cyclic permutation graph. It's just a 3x3 permutation graph. 1 goes to 2, 2 goes to 3, 3 goes to 1. As simple of a permutation as I can get. And so here, I'm creating the graphical model. Now, this in the graph package, by default, there's not going to be any checking to see if I have a cycle, which may be good. That may be good, maybe bad, depending on your project. And here, I'm attempting to make it into a BN_learn object. And you'll notice I got an error. But if I say check cycles equals false, it will go ahead and do it for us. It will knock it out and everything, Now, if I attempt to drop this model into other functionality within BN_learn, errors are going to get thrown and I'll have problems. But if this is what I want, I have that option. The next package to talk about is the Igraph package. This one has been used for network analysis, and it has some hypothesis testing, and it has some visualizations that you could use. So it's got extensive selections for creating and generating graphs. manipulating nodes and arcs, highly customized plotting facilities. I like the the Igraph Viz package more, honestly. And so this has got so much utility in it that Learn wants to connect pretty nicely with it. And so it's got a different network structure. Remember, every package has its own network structure, which is a pain. But how this, one way to approach this is that if I can get the adjacency matrix, I just drop it in, boom, I've got it. And so in the Learn package, AMAT is my adjacency matrix format. And here you can see this is how it codes up the edges and the arcs. Equivalent information, different presentation, equivalent, storage, but different formats. And so here we can plot it and get, see what's going on. Now, undirected arcs are exported as pairs of directed arcs. So if I have an undirected edge between two variables, how it's going to get exported is as two directed arcs in opposite directions. So it's redundant. So if we were to go through and pick through here, we probably would find, an edge in there. And so the adjacency matrix technique is good for going from Learn to Igraph objects. And when I have it undirected, it goes like that. If I just say everything's undirected. And so my adjacency matrix needs to be a symmetric matrix when I do this. And once again, if I want to import from Igraph to the Learn package, once again, it's going to be the adjacency matrix that does it for me. Now, this can be a very large matrix if it's a large number of fields. Another way to tackle things is if I start, let's say I want to build a graph. What I can do, I can build a graph with all the variables, but no connections between them. And so what this does, all of my variables are sitting unconnected to each other in the graph. If I put in this command, I can specify what the adjacency matrix will be, and boom, we can get it. So here on this step, there was no connection between the variables. We can see now I have all these connections. The G-Rain package is the next one we'll talk about. I know that this is feeling very redundant. I feel like this is not the most exciting lecture of my life, but when I need to hop between packages, this is one of those super frustrating moments that you could be spending a lot of time on. So there's good information here. I hope that this will save you from hours and hours of frustration if you use graphical models down the road. All right, so the G-Rain package, grain, however you want to say it, provides implementation of exact inference in R. All right, so there's high bars for this one to be doing exact inferences. If you want to read the textbook on this, on what the criteria is, I think if we are in like the business world, it's not going to be, we just need best information to guide our decisions. Currently, this exact implementation is only for discrete, all discrete random or all discrete variables in our Bayesian network. And the main structure of the grain package is the grain class, which stores a fitted Bayesian network as a list of conditional probability tables, much like the be and fit objects, but a different format. And so this sets it up that we can set evidence and query grain to get our posterior inferences based off of belief propagation. Belief propagation is that seeing this variable changes this conditional distribution, changes this conditional distribution, changes the one we're interested in. And so we can use the asGrain function to convert a Bayesian network to a grain object. You can see that some things happen along the way. When I build my model, if I don't have enough data points for pairs, so realize if I have 10 variables, and let's say, and I've got all these connections. Let's say that I've got 2 different variables that are connected to each other, and both of them have 10 levels. They're discrete. 2 variables connected to each other, each with 10 levels. What size is my contingency table going to be? It's going to be a 10 by 10. That's how many entries? That's 100. Is it possible that some combination will be missed? If let's say I had 1,500 data points that I'm working with, and I have 100 by or a 10 by 10 contingency table that needs to be fitted. Some cells are probably going to get missed, more than likely. Like best case scenario, I would have 15 in each one of those cells, right? So that would tell me that like convergence might be an issue. And so what would happen is that more than likely we're going to have some blanks. Some pairs did not happen. And so when the pairs don't happen, what all this junk is saying is that it's going to just assume that we have the uniform distribution because it doesn't know any better. It's just going to go uniform distribution, fill in the blanks, I don't know otherwise, and go with it. So that this is good and bad. If I need to keep moving and I need to just get a model that is working pretty well, that's good. But it's also like fitting in stuff. Remember that whenever I'm doing imputation, whenever I'm filling in stuff, I'm making up fake data. If I'm using fake data, that could be bad. So only discrete networks can be exported since grain does not support networks with other parametric assumptions. Now, the grain package does not allow for conditional probabilities to be not a number. I mean, that makes sense, right? I mean, this happens when estimating them via maximum likelihood, and some parent configurations are not observed in the data. So imagine that I have 1,500 data points and there's a connection between 2 variables that each has 10 levels. Then I'm more than likely going to have blanks, not numbers, and there'll be issues. One way that we can get around this is that during my data prep phase, if I bin down to fewer levels on my discrete data, then I run much less risk of having like blank pairs. All right, so now we want to go the other way. So we just looked at taking a be and learn object and putting it into grain. Now we want to take a grain object and convert it over. And nicely, it's just as bn dot fits. And all equal, it will go through and detect if there's a difference. And hey, we notice that there's a difference in the probabilities for the ECO2 column, but remember that was one of the uniform distribution ones, so that makes sense. Everything else jives. Now, so you know, it'll get as best of a connection as it can, but if it filled in the blanks on something, you know, it'll be out there on one side, but not on the other. And now if I'm just concerned with the structure, you'll notice that the structure stayed the same when I run the all equal. The set evidence function is the one that we use for establishing what the particular values are when I do my conditional information. And as.bn.fit disregards any of that evidence that we've already set up inside the grain object. So that is something to be mindful of, that if we went through, if I built a grain object and I set a particular value. So let's say that I have a model and I know that I'm only going to be working with one variable set to a particular value or multiple variables set to particular values. I can make things run faster and easier to interpret by setting it to that particular value. If I do the conversion over, that restriction on the conditional probability gets kicked out. Any questions about this? All right, then if there's no questions, we will call it a night.
I have a question. Final project for
Yes.
fall apart on page 10 or something, or
Yeah, 5 to 10 is fine. Don't kill yourself. You know, I'm quality before quantity.
sure.
You know, I'm your target audience. Know your audience. I'm just looking. I'm looking for any type of quality data work. I don't care if it's from another class. I don't care if it's from work. I don't care if it's like a volunteer project of yours and you're just, you know, taking something that you have to do anyway for work, slap it on a piece of paper and submit it. I'm cool with that. More than anything, I just want to see you actively using the material. You know, this is a second semester course. You know, the data mining 1, data mining 2, and in the data science program, there's courses before this. So I view this as more of like a capstone project for you. I am big on visualizations. I am huge on visualizations. If you want to make me happy very quickly, it's going to be dress well, guys. Dress well for your presentation. And the second is do visualizations. I like to be able to just look through, look at your graphs, boom, boom, boom. I know what you're trying to tell me. And I can just skim over the words. That's the best advice I can give for that. You don't need to include your code in your documents. A good rule of thumb for your code is never compute in public. Even though you'll see me do that in class is kind of different. You know, learning how to use a code is one thing. If the point of your project is the code, let's say that there's a research paper that theoretically shows that something would work, but no one's implemented the algorithm yet. that is a perfectly acceptable project. Then your project is the code. Put your code in there. If you're presenting to people with a coding background, show important chunks of code, but don't show the whole darn thing. If you're presenting to people who have no coding background, never show any code. And if they ask, you can show it to them, but showing them code is like showing them math on like a bunch of algebra equations to average people. It just doesn't go over well. Other questions?
About the homework, Professor, I'm still confused with this core of the model. For this core function from R,
Mhm.
I see that we compare the net with the data that specifically in the library reference that we have. So we are comparing the first parameter is model, the second one is the data, like a test data to compare it.
Which function?
BNR score.
Okay. Let me pull that up. Zoom people, can you see my screen?
Yes.
Is this one?
Yes.
Okay, so what this will do. All right, so the part you want to focus in on is this. It is the bottom. Oops. Okay, they've increased the documentation since I've been here for a bit. All right, you can use a score function. I find it's just better to use, especially for reading down the road. I use AIC or BIC or the log likelihood. So the log likelihood, it estimates the likelihood, from a multivariate distribution. Works great. So you pass it the graph that you have, and then the data that you have, and it gives you, a log likelihood. And so there, the bigger the log likelihood, the better. Now AIC, BIC, what these do, these take the log likelihood that we just talked about, but then subtracts off a penalty for the number of parameters that we have. So the more edges you have, the more arcs you have, the more of a penalty gets hit. The difference between AIC and BIC is the size of the penalty. BIC hits with a heavier penalty for each parameter. So BIC is going to favor simpler models. All three of these will use log likelihood in the calculation. Which one's the right one to go with? I usually feel like BIC is too heavy of a penalty. Like the algorithm chooses to kick stuff out more than I would like. So I usually go with AIC, but whichever one you go with is right. You can control the penalty coefficient here if you want and adjust it to what you feel is best.
I was trying to do it in Python, but we don't have no score function for deep learning Python. There's just a compare networks.
Yeah.
So,
Can you get the log likelihood off of it?
no,
Okay.
really consider to do the homework. I try to find some.
So the purpose of it is not for you to do it this particular way. I want you to operate like, okay, my office uses Python and I need to check, do I have a good model? It's not so important how you check your model quality, is that you check your model quality. Like you and I are doing supervised learning on projects. Maybe I choose mean squared error. Maybe you choose mean absolute error. Honestly, you're probably going to get like the same conclusions. Maybe, there might be a little bit of difference, maybe like two comparable models, your technique would pick one, mine would pick the other, but they would be comparable, which means the results would be probably, about the same. I don't care so much that you do a particular technique to check model quality, that I just want you to check model quality. I want that to be something, I build a model, I check it. I do something, I check it. Because that's absolutely critical for actual use. So if you find some other metric, just go with it and write that in your homework. Yeah.
Dr. Smith,
Did somebody ask a question? My speaker is not picking people up very well.
can you hear me at all?
I can hear you, but barely.
Okay,
Could
let me
you
like
like be
yell.
loud in your microphone?
So I scraped Twitter for my project on Roe v. Wade tweets because I know the UCF portal only lets you do like the prior 2 days of like tweets. So I know that this is something that's still happening, like, and people are still talking about it. So I was like, I'm gonna get the most amount of stuff from this. But when I'm doing sentiment analysis on it, and the number one like feeling or sentiment was trust. And I feel like that's not very accurate. So I didn't know if like I did everything right, and like I got like a lot of fear and a lot of like other ones that were like appropriate, like anticipation and stuff like that. But trust being like the first one kind of like shocked me. So I didn't know if like how I could, counteract that or fix it or.
Well, I mean, my response to that is, roughly speaking, half the country votes one way, the other half of the country votes another way. And it might just be that half of the population, like the trust half, is getting picked up in that.
Okay.
So I think I would not dismiss that outright. I think you're just, I would conjecture that you're picking up the other side of the aisle off of that one.
Okay, thank you.
Other questions? I love it when data surprises you. When you get like, oh, wow, this is going on. It's all right. If there's no more questions, then I will go ahead and we'll call it a night. See you next.
Hello, Professor.
Yes.
I have a quick question. I'm taking a project on stock market analysis.
Okay.
But I'm not getting too much visualizations on it, and the algorithms which I'm running, they're not the classification algorithms cannot run. There are 2 to 3 algorithms which can I work on it, but what predictions I'm doing on it, exactly what the actual price it should be given, it is not giving that much correct. So I should go ahead with 4 to 5 algorithms, or I need to change my topic.
It's acceptable for this project to proceed forward with what you're doing. How I want you to answer the question for this is, how would you do this if this was your real life project? Like this, if you were at work and you were given the tasks that you're working on, how would you tackle these difficulties? Honestly, there's so many times that the data just doesn't work out the way we want it to. And I don't want to give like a prescribed answer. In a lot of ways, I want to put you into that uncomfortable feeling of what should I do? I don't want this to be like, a college algebra class where there's only one right way, there's only one right answer. So I think, so my understanding is that I had trouble hearing through the speaker, is that you are having difficulties with getting accurate forecasts on stocks. Is that right?
Yeah, I'm getting forecasting means like visualizations I'm getting, but not too much. That you told that you need more visualizations, but I'm getting at least 5 to 6, not more than that. I can show you, but
Okay.
so that is why I was asking like I should go ahead with this topic or I should change my topic then.
I think you should go for it. This is interesting. This is good, juicy stuff. Just, present it the way you would if like you needed to present at a job interview.
Okay.
And, so, when it comes to like how many visualizations do you need? Just basically ones that are informative. If you have a visualization, you need to be able to articulate why that's in your presentation. And it should be obvious to you pretty fast. So if there's something like I did a visualization today for work showing that this one variable, if the variable gets to be 3 or above, then the probability of things being on time just absolutely plummets. And the contrast was visually very striking. And so for that plot, it was very obvious why that was on there. Another plot I did at my supervisor's request was how many open and closed cases we had per quarter. Well, when you look at it, it's just a very dull, boring one. It doesn't really show, like no one's going to lift their eyebrows when they look at it. It's basically saying quarter one has as many open and close as quarter two, as quarter three, as quarter four. Nobody's going to be interested in that. That's not going to raise eyebrows. I would want to remove that. And so if you look at a visualization and you can say the conclusion you want to draw from this visualization is XYZ, then that's a good visualization. If you see something and it may be mathematically correct, it may be a sound presented visualization, but you don't have a sentence to say what the conclusion should be, it's probably one that should be removed from your presentation.
Okay, sounds good. Thank you, Professor.
Professor, I have a
Yes.
question too.
Yes.
My project is about using convolutional neural network to detect Trojan image.
Okay.
So I'm basically training around more than 20 models.
Okay.
So for the document, you said you don't want us to show all the coding, all the training process of my model. So I'm thinking I just show, because I do a lot of changes, I do a lot of modification for each model, try to get the best result. So what would you want me to do?
How I would tackle that is that I would, something that I would do is I would just put down like, I would make a table that describes that describes each of the models. So you've got 20 of them. You'll have, different activation functions. You'll have different, number of hidden layers. You'll have hidden networks, skip layers, bias, stuff like that. You can, put in a table like what each model was, some description, and you don't have to be like super precise, but something that just says that distinguishes each of them. And then you say like, oh, here is my performance metrics for training and performance metrics for validation, performance metrics for tests. And so then it can be, it's real quick and easy to check and see how each of them compare. Because does that answer your question?
And because I plot those learning curves, some of them apparently they are overfitting. So, but putting all those images gonna take a lot of pages.
Yeah, don't go crazy on the amount of stuff you put down. It's okay to summarize.
Okay, I got you. I will see what I can do. Thank you.
Good questions. Good questions. Any other questions?
Professor?
Yes.
So I have this question. So when we prepare the documentation, as you mentioned that we should not, upload our code file. So is it something that we can, we can add those snapshots in the document and then explain about it?
Yes, that's acceptable. You also have the option of uploading the code file itself, but
Mhm.
I would not put, I discourage you from including like your raw code in your documents, because that ends up just being like just wasted pages. I will,
Okay.
because more than likely, anybody that will be going over your code professionally, it would be like a peer review or maybe your supervisor double checking your coding, or
Mhm.
possibly like somebody who's taking over for your stuff, but it wouldn't be somebody who's reading your code. They would be using their computer, actually interfacing with the code themselves.
Okay. So can we just, put a snapshot of the visualizations and then let you know like what we achieved
Yeah,
with the problem statement that we are dealing? Okay.
I find the best way to put visualizations into things is to
Mm-hmm.
use PNGs. I find that, and this is true for Python and R. I think that most visualizations look best if they're saved as PNGs and then put in your document. But however you want to do it, I'm not going to grade you on the quality of your visualizations. I just like to see that. Oh, okay, when I say quality, I'll grade you on the quality of your visualization from an informative point of view, but not from a beauty and aesthetic point of view.
Okay. Thank you. I got it. Thank you, Professor.
Thank you.
That helps. Yeah.
Yeah, you can do what's easiest. If you don't know what to do, ask yourself, what would I do at work? And that's the way I want to see it.
Okay, Professor. Thank you.
Any other questions? Good stuff, good stuff. All right, then. Go ahead and start shutting stuff down. Give people a moment to chime in. All right, then I'll go ahead and close it out. Have a great week.
Thank you, Professor.